Hello, welcome to Calculus 2. Today our first lecture is about lengths of plane curves. To estimate the length of a plane curve, we don't want to use arcs that are circular or parabolic. Instead, we're going to estimate using line segments in different directions that will comprise a curve. We're going to utilize the Pythagorean theorem that tells us that the length of a hypotenuse is calculated by the formula: the sum of the squares of the legs equals the square of the hypotenuse. So you see, we can use a right triangle to calculate the length of delta S, which is the line segment that's used as part of the approximation of the curve length. And we use the distance formula, which is the Pythagorean theorem applied to the Cartesian plane. Delta x squared plus delta y squared equals delta s squared. As you can see, delta x is just x2 minus x1, and delta y is just y2 minus y1. Now, the lengths of delta x, delta y, and delta s are going to be very small. We're going to let those lengths approach 0. So we can replace delta x by dx, delta y by dy, and delta s by ds. These are the differentials which will help us to come up with a formula for the length of a plane curve. Recall the definition of a differential. The differential dy is f prime of x dx when y is f of x. This differential will help us to estimate the length of the curve. Now here's our formula for ds in terms of the distance formula and the Pythagorean theorem. And we need to factor out dx squared in order to rewrite this formula in a useful way in order to find a formula for the length of a curve. This is mostly just algebraic manipulation. So this is what we do. We factor out the dx squared. The square root of dx squared is just dx. And this helps us to simplify our formula in terms of the derivative dy dx. So now we integrate ds over the x limits from a to b, and we can write the formula for the length of the curve from a to b, x values a to b, as the integral of the square root of 1 plus dy dx squared dx. So if we know y as a function of x, we can calculate dy dx and use this formula to find the length of the plane curve y equal f of x from a to b. So this is the picture. We have the graph of the function y equals f of x on the x interval from a to b. And we're going to use the formula y equal f of x in order to calculate the length of the curve. And now instead of writing dy dx, we're going to write f prime of x as follows. And here we see the formula with f prime of x replacing dy dx, which is the critical connection of the derivative to the differential, which we've used as our mnemonic device to remember the formula for ds. So we can now see that by doing a little bit of algebra differently, if we factor out the dy squared from the formula for ds, we can actually get the expression of ds in terms of the derivative dx dy, where x is a function of y, and y has values between c and d. So this will allow us to find the length of a curve when x is a function of y. And we can see here then that the length of a plane curve is the integral from c to d of the square root of 1 plus dx dy squared, dy. And here, x is a function of y, x is equal to g of y, and the limits for y are c to d. So now we can rewrite the formula for ds in terms of the parametric equations. X equals f of t and y equals g of t. And we're able to find the length of a curve which is expressed in parametric form for t between t1 and t2. Now let's take a look at an example. We want to find the length of the curve y equals 1/3 x squared plus 2 to the 3 halves, where x goes from 0 to 3. Our first step is to calculate dy dx, the derivative. And you see that after simplification, dy dx equals x squared plus 2 to the 1/2 times x. In our example, we found dy dx. Now we find dy dx squared, and then we add 1 to it. And we see that dy dx squared plus 1 equals x squared plus 1 quantity squared. So you see ds, the element of arc length, just becomes x squared plus 1 dx, and the length is the integral of that from 0 to 3, which is x cubed over 3 plus x from 0 to 3. If we plug in the limits, we get 27/3 plus 3 minus 0, which equals 12. So the length of this curve from 0 to 3 is 12 units. Let us now look at another example. Find the length of y equals x over 2 to the 2/3 from x equal 1 to x equals 2. We see that the derivative squared is equal to 1/9 x over 2 to the negative 2/3. And so the length of this curve from 1 to 2 is the integral of the square root of 1 plus 1/9 x to the negative 2/3. These are for limits for x between 1 and 2. And we'll be learning how to do these integrals in Chapter 7, Methods of Integration. This concludes our lecture on the length of a plane curve. Practice the homework problems and get used to working with ds in different forms. Thank you.